but definitely not least, this week we're going to be identifying what I think is the best rock, and there are a lot of these in Florida. Woo! Sedimentary rocks. This bad boy's a heavy crinoid grindstone, one of my favorite rocks I own. Anyways, let's get started with some identification. Geology. Like the previous lab, I'm using mostly a hand lens and some HCl to identify these rocks. Sedimentary rocks are rocks that form from the accumulation and consolidation of sediment, and it's usually in layered deposits, as you can see in a lot of these pictures of sedimentary rocks in the wild. Now, sedimentary rocks are super neato because they can tell you a lot about the environment that they were deposited in. So hopefully, hey, that's me climbing on some. So hopefully that'll become clearer as we do the identification. So starting off, here is the ID sheet for sedimentary rocks. Like the others, you're going to start off by narrowing it down by category. First category being composition. And there's going to be 3 main compositions. So starting off up here at the top, you have detrital sedimentary rocks. They're going to be made from weathered material. Moving down, you're going to have biological sedimentary rocks or biogenic. Then further down, you're going to have more chemical sedimentary rocks like evaporites and crystalline material. So, scooting around here. Okay, so first in this top category, detrital, what do we have? So when you're looking at a detrital sedimentary rock, it's going to be made from rock fragments, quartz grains, or anything that's derived from a weathering process, whether that's mechanical or physical. Moving down, you have biogenic, and that could be plant fragments and charcoal, that kind of thing, peat, coal, and then you have shells and any sort of calcareous microfossil, anything that effervesces in HCl. You're going to use a lot of HCl in this lab. Okay, and moving down, notice oolitic limestone is technically in the bottom category, but it's going to still fizz with HCl. Cool beans. And as well as travertine. So next you have chemical sedimentary rocks, specifically things like dolostone, rock salt, or gypsum. A lot of these things are going to be evaporites. So next you're going to go into the texture of the rock. This is going to be your second step. So let's say we're up here in the top category. You can have angular grains. I'm trying to find the thing. So yeah. Angular is based off the pointiness kind of the sediment in the rock. So you can have very angular stuff, very pointy. You wouldn't want to get poked with something very angular. Subangular, they're not super duper angular, but they're still pointy. And then rounded, they're round. Like they ain't gonna hurt you if they like stab you. I mean, if they're thrown hard enough. But hopefully that doesn't happen to you. Anyways. So up here, you can have some that are rounded, and then you can also have different grain sizes. So there's roundness and size. They can be made from quartz, feldspar, rock fragments, anything they're made with these different kinds of minerals. Flashback to mineral lab are going to be classified as different kinds of detrital sediment. Okay, so moving into this middle category, again, what are your grains like here? You can have something in this top part where there's plant fragments or charcoal in your sample. So peat might have some roots, and lignite is dull, dark, and there might be some fossil plant fragments. And then bituminous coal is going to be sooty or bright coal. So moving down here to this part, okay. So this is going to be your cool fossil boys. And it's going to be, again, varied on grain size. You could have big, huge shells like in coquina, or you could really not see the little fragments of calcite at all, as with micrite. Again, acid is your friend here. Some rocks look very similar, and acid's the really only way to completely tell the difference. So if we move down to the very bottom with these mineral crystal rocks, you can see these top two, travertine, oolitic limestone, they're going to effervesce with HCl. And then travertine, dolostone, rock salt, and gypsum are all evaporite rocks. So they've formed from evaporated solutions. And then notice again, acid's really important, like with micrite and chert, because they both are going to have no visible grains, and they're going to be microcrystalline and really teeny. But the real way to tell the difference is acid. Micrite will fizz and chert won't. So why these rocks are so super sick, nasty, awesome is because sedimentary rocks can tell you a lot about the environment way back when these rocks are forming. So chemical rocks, biochemical rocks, detrital rocks can all tell you different things. And even the grain size and what they're made of especially are going to tell you, like, where did it come from? So let's say you find some sandstone somewhere out in the wild and you're like, oh crap, I wonder what this was at first. Well, maybe it was a beach sand or something and it got lithified, turned into some rock. And then, or maybe, you have some shells in there and fossils. Oh, so maybe that was also on the coast, but maybe a little deeper out in the water where there were some shelly organisms living around there. Okay, what about if you have some really fine grained stuff, some muds or shales, and maybe they were deposited really far out in a deeper marine environment or somewhere where it traveled far away from the mountains. Or you have some coal or some peat. Maybe it was originally a peat bog. Even the boring seeming stuff like sorting and roundness and grain size are really important, because if something is really well rounded and really small grain size, it means it was probably transported really far, so it had a lot of time to get the smooth round edges or to break up into teeny pieces. Right now this is scrolling through a sedimentary rock picture I took in New Mexico at field camp, and it really shows how the sedimentary environment changed. About here we hit a conglomerate layer, so maybe that was some river or close to a mountain sediments that were really big and got deposited there, and then you get into some finer grained stuff. So could that be a beach or the outer edges of a river? Cool stuff if you ask me. Okay, enough of me nerding out. Let's get into the example. So here she is. So she's got lots of shells, lots of nice shells. Oh, look at that one. You can see that one really clearly with your naked eye. And the fragments are really big too. And if you use the hand lens, you can even see that that is really a shell there. A really cool shell. Sweet. Okay, look at those cool shells. So we know that it's not up here, it's not detrital. And we can see stuff, so it's not down here in this like crystalline stuff. And yeah, it's not here. And it fizzes with HCl. And you can see the shells and stuff. And there's not really any teeny ones anywhere, so we have coquina. Yay, fun fact, something about coquina that you might have learned if you went to school in Florida in 4th grade and they made you go to St. Augustine, is that they built a whole heckin' fort in St. Augustine out of this stuff, out of coquina. And they were like, we need a really strong fort, and look at these strong seashells that make sea animals strong from other predatory sea animals, so we're gonna make a freaking fort out of it. And then they hadn't really ever made a fort out of coquina before, so they were just testing it out, and it turned out that it actually was really good because coquina is absorbent, not unlike toilet paper, and the walls just absorbed the cannon blows from the British, and they were all fine and dandy for a while, I guess. So yeah, coquina is some tough stuff. Anyways, your turn.